Black math! Give me some math and I'll give you some flack. Black math!
We're going to talk about vector decomposition.
Yes.
Okay, what's composition?
Oh, like understanding things. Like your reading composition.
No, that's comprehension.
Oh,
So what's composition?
writing.
Composing, like putting stuff together. So decomposition would be taking it apart. Okay. So decomposing a vector means to separate it into two vectors, which, when added, result in the original vector. Okay. So when a vector is decomposed, it is split into horizontal vector and a vertical vector. Okay. So basically, we have this vector, for example. Decompose each vector. Here's example 1a. Here's a vector in. So, what do you think is going to happen if I decompose this? What's going to happen? How far right does it go and how far up does it go? Okay, so here's what we're going to do.
Would that mean you, like, if it's being deconstructed, would it be negated or no?
So the x vector, not negated, but the x vector would be 2 to the right. So basically it's 2 and then up 0 because it's just going right or left. It's not going up or down. And then the y vector, so you can do v subscript y, would be 0, 3. Does that make sense? So it's just like you don't want to cut through people's yards, so you're going to go around the block. Okay? Yeah.
I cut through people's yards sometimes. I would cut through people's yards.
Well, then do that vector. Okay?
Because I need to go through people's yards.
You're fine cutting through the yard. I mean, that's just a different vector. I'm just talking about decomposing a vector into going around the block. Okay? So you go right or left first and then up or down. Does that make sense? So that's decomposing a vector. Let's try it a different way. Let's try this. Let's try example 1b, and we don't have it in composite form like this guy. We have it in this. The vector v has a 33-degree angle and a magnitude of 7. Okay, so I'm going to roughly draw it right here. So 33 degrees is about right here, and it has a magnitude of 7. So how do you think we can find the x vector and the y vector? Any guesses?
Can't you use one of the trigonometry functions?
Yep, we would use a trig function.
Oh,
What were you going to say?
I don't know what the function is.
Okay, so remember we need this vector and we need this vector. We need this length and this length. And like we could use a Pythagorean theorem if we had one more side, right? If they gave us one of those, then we could find it using the Pythagorean theorem. But we don't. We just have an angle and we have the hypotenuse. Okay, so let's use trig. So look, let's call that y and this x. That makes sense because we want the x vector and the y vector, right? So basically what we're trying to figure out is this coordinate. Where does that end up? Well, what trig function would work to find y if we're only given 7?
Do we have online students in this class?
We do today. Yeah, and Caden is an online student as well. Okay, so
Oh, there's not.
Okay. So let's use trig. Look, what side is y to 33?
Opposite.
It's opposite. So what?
Opposite over adjacent.
So we don't have the
Opposite
adjacent
over
though.
height.
So what trig function deals with the opposite and the hypotenuse?
Oh, opposite.
And
Oh,
the-
TOA. No.
Hold on.
So,
Yep, sine, right? So sine of 33 equals y over 7. See how we got that? So you could have, and to find x, you could use cosine of 33 is x over 7, because that's adjacent to 33, right? So cosine of 33 would be adjacent over hypotenuse. Okay, so let's figure that out. Well, we have to solve for y, so let's just multiply both sides by 7. So y equals 7 times sine of 33. Anybody have sine of 33? Multiply by 7. On your calculator, you can do sine of 33 multiplied by 7, and you get,
I got it.
what is it?
Give me a second.
I thought you said you had it.
33. Sine of 33 times 7?
Yeah,
Isn't it like 4.02168833?
no, that's not what I got. But here's what the book said, 3.81.
Oh, it's sine of, yeah.
Okay, so 33 sine. If you're doing it on an iPhone, you have to say 33 and then the sine button and then times 7. And you should get 3.81-ish. Okay, now x is going to be 7 times the cosine of 33. You got what? Let me, I can double check my answer too. So all I'm doing
33.
is going 33.
Yeah, I'm getting 4.02.
Okay, I think you just tried to,
Sine of 33 times 7, right?
I think you're, something's not working here, girls. Did you send, how many did you, so you did 5. Did you already do them all?
I'm sending 5 right now. Oh, now it's sending to today. Okay. Wait,
No, I don't want those.
So if you tried to just send me something, it got caught up with the, my phone tried to intercept it.
Have you all tried sending me
I don't
one by
want
one? Because the files might be too big.
No, they're fine. It's just that I can't use my calculator. So
Wait, let me
Would
use
you
my
like to see the
calculator.
steps I went
You
through
guys
it?
are want me to
That
send
right?
So if you have,
Because
if you don't have
33
an
is like
iPhone, then don't do it that way. So you do sine 33. So if you, that's.
When
this
I
is
do, but when I do sine 33 times 7.
No. You're not doing 30, sine of 33 times 7. You're doing sine of 33 times 7.
Please raise your
Sine of 33.
I got 3.81.
hand.
There we go.
Does that make sense? So you just did the sine of whatever 33 times 7 is. Don't do that. Okay. So that's 3.81. When you do the same thing with cosine, you get 5.87-ish. Okay. So here is your the vector decomposed is, let's see, 5.87 comma, or that's comma 0, right? So you go right 5.87. So this is the x vector, and the y vector is 0 comma 3.81-ish. Okay.
Let's go.
Great math lesson. I really learned a lot.
Okay, all right. Moving on. So then this allows you to add different vectors after you decompose the vectors. So after you do that, you just add the x vectors and add the y vectors. So if you wanted to add two that are in this format, then you have to decompose it first and then you can add them, okay? So let's do an example of that. So if you can understand this next step, this next example, then you understand this unit, because this is, it's not complicated, it's just a lot of steps. Okay, because you have to decompose vectors and then you have to add and then you have to recompose, I guess. Sometimes you have to put them back into the original format. Okay, so let's do vector V has a magnitude of 4. So I'm going to do this. So this means like the magnitude of something is 4 and at a 23-degree angle. Okay. Okay, vector W has a magnitude of 7 at a 61-degree angle. Okay, so if I were to sketch this, here's what it would look like. 23-degree angle at 4, so maybe 4 units there, 23 degrees. And then 7 at 61 degrees would look kind of like that. So there's 7, there's 4. So there's another, it goes 61 degrees. So it'll kind of end up there. So here's what we need to do. We need to just separate this into 2 different problems and decompose both of them. I just canceled something because
You're airdropping. That's the sound.
okay, so here's one vector, 4 at 23. Okay, so I need to decompose it. So I need to find the x and the y, right? Okay, how do you find the x and the y? What did we do? Y equals basically 4 times the sine of 23. And x equals 4 times the cosine of 23. If you want to work it out and say sine of 23 is y over 4, and then just solve for y by multiplying by 4. Either way, you'll end up right there. So if someone wants to do that math for me, that'd be great. Sine of 23 times 4, and then cosine of 23 times 4.
Y is 1.6.
1.6 what? Or 1.69-ish? Okay, and what's cosine of 23 times 4?
3.68.
Okay, so I got 3.63 in the book here, so that's close enough. All right, so here's what we got. We've got, so that means our y vector is 0, 1.69, and our x vector is 3.63, 0. Okay, so we decompose that vector. Let's decompose this one. So you guys try this. So you probably, it's nice to draw a diagram. I just think it's easier. So this is 7. So we want to find x and y. This is at 61 degrees. Okay, so what do you have to do to find x and y? You guys doing it? That's basically it, right? So x, you have to find it's the cosine. So x is always cosine, y is always sine. Okay. So it's the hypotenuse times the cosine of whatever angle that is. If you want to work it out like this, you can. Sine of 61 equals y over 7. So y is going to be 7 times sine of 61. Same thing with cosine. So did you guys get this? What'd you get?
Y, I got 6.12.
Okay,
And X, I got 3.39.
good job. All right, so here's the x and y vectors. So the vector of y is 0, 6.12. And the vector of x is 3.39, 0. So now I'm going to add the vectors. Look at this. So Vy plus this other Vy is going to give us a number. So actually, this is vector W. So I'm going to just do this. Does that make sense? Okay, so now I go Vy plus Wy equals 0, add those together, 7.81, right? 7.81.
That is 5.
Now I'm just adding 1.69 and 6.12.
Okay, no, I was looking at the other question.
Okay, so now I'm going to do the x vectors. And that's just 3.63 plus 3.39. So that is going to give me 7.02, 0. Okay, so now what do we got? Now, if I were to draw this vector, it would be over 7 and then up almost 8. So it looks like this. So this is 7.02. And this is 7.81. So I want to know what that is. How do I find that? I'll give you a hint. Pythagorean theorem. So I need to know that distance. So this is going to give me basically the W plus V plus W vector. Okay. This is going to give me the result. Pythagorean theorem that. So a squared plus b squared equals c squared. So square 7.02. I'll do the math for you. So you get, and then you take the square root of it and you get 10.5-ish.
Super cool question. It's about geometry. So I'm looking on like your names for like geometry.
Uh-huh.
Oh, never mind. I found it. I wasn't seeing the practice test video, but it's like all the way at the bottom. And it's split in 2.
Yeah, and it's on Schoology too.
Okay.
I put a link on the practice test and the test, I think. So there
Okay.
should be a link to the video on that.
They're very funny. I laughed at the videos.
Yeah, they're good. I put a lot of work into them.
I like the ones I'm featured in.
Oh,
I'm sure.
these are better because they're better quality, good music. I think I talked about my mom at one point. Maybe, I don't know. Anyway,
I didn't.
You must love your
It's
mom.
very good. Trash is very good.
I like my mom.
I like my mom too.
I'm pretty sure my
I like
mom's
your mom's
least
too.
favorite.
okay, so here's the deal. In order to add 2 vectors, you have to decompose them. So you have to find their x and y coordinates and then add the x and y coordinates together. And then once you do that, you have to pythag the rest of it out to get the total magnitude.
I don't like
Okay.
the word you use.
The bag.
Pythag it.
I don't like
Okay, I didn't like it as soon as I said it. Pythagorean it.
That's not a word.
Yeah, you can verb anything. See what I did there?
Just don't use Anne Frank as a verb.
What? Why would you use those?
Like,
I'm gonna shadow.
it's like if a dog needs like shelter for the night,
I'm gonna walk.
but your landlord doesn't like dogs, someone could say, I
Okay. I mean, I think that's bad. I think it's bad, right?
can. You can't,
I don't think
you
so.
can't use anything as a verb.
Something's only bad if you let it be bad. Okay.
Okay, there is one more example before the real life application, but I used to have a Bible called the Life Application Bible. So every time I say real life application, I think of that Bible. And then,
I
like,
used to have a Bible with
used to have like
you know,
devotional questions.
Book of the Bible markers.
Oh,
I still have it at my house.
you should bring it.
Okay, so you can do, it doesn't have to just be two, you can add 3 vectors. The one thing that I was gonna just mention is what if it's at 90 degrees? How do you figure out a vector at 90 degrees? So a vector, what if, let's call it vector x. The magnitude is 11 at 90 degrees. What does that vector look like?
It's straight up.
Yep, it's straight up. It goes straight up. So how do you calculate the magnitude of that?
You don't.
There's no x value. It's just 7y.
No. What? 7y?
Yeah.
It's 11. So it just goes up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is what the vector looks like. It looks like that. And guess what? You don't need to do any trig or anything because that is 11. So if a line is completely vertical, that's really easy because the magnitude, so basically your x vector is 0, 0. Okay, so your x vector is 0, 0, and your y vector is just 0, 11. Okay, so those are easy to add. You don't have to add any x value, you just add the y value. Okay, so that you might get something like that. All right, lesson 90.
That's like the longest question in college. I don't think I'm long enough. No, oh, no.
Okay. All right, we're going to talk about composite transformations.
I think that's like yeah, but I hope that's the video. Do you by any chance want to just not make me do the last practice test?
Okay, so composite transformations. Remember, two or more transformations that you put together. So you could slide something, you could flip something, you could rotate something, or you could do all of them together. That's a composite transformation. More than one transformation. Okay, so let's try an example. Here's example 1. Okay, so reflect triangle ABC across line M, then translate it along vector V. Okay, so obviously you're going to need some more information. They give you a diagram. Okay, so here is a triangle. Let's just draw, this guy is line M. Here's line M. Here's vector V. Okay. And then here's triangle ABC. Okay, first step, let's reflect triangle across line M. Anybody want to come up and try it?
What's the name? What are we doing?
First step
Oh, we're
is to
reflecting.
reflect triangle ABC across line M. Anybody want to try it?
I think I'm gonna do it. I
Okay.
wasn't really paying attention, so I don't really know what we're doing, but that's
Well,
okay.
what would you think a reflection of that triangle would be
I don't
across
like that
line
we have
M?
memory. So it would be down here, right? Because it would reflect.
Yeah, but
Would
it's,
it? Would it really?
but you don't have to go that way. This is like the mirror. Okay, so, yeah, so just draw a reflection of that. So you have to draw it backwards.
Backwards. Okay, hold on.
I could do that.
That little curve, so I remember which line it is. No, don't want to do that. I want to go.
Yeah, it got a little smaller, but sometimes that
I didn't
happens.
want to draw that big.
But you're good, you're good.
Wow, it's hard to
So
do
that's the
that
basic
way.
idea, right? You're going,
You erased it.
hey, well, it's not that I didn't appreciate it, but. So
I'm
see how
supposed to
that's,
leave now.
see how that's reflected across line M. Raise your hand if you see that.
Actually, I think hers was better.
Thank you, I agree.
It was more the shape. Yours is
Okay.
better.
So now what does it mean to translate along vector V? What do you think I'd do with it next?
I did put it on the line.
Not on the line.
Oh, well.
Along the line.
So that vector V is just a reference. It just says go down that much. So from here,
That's what I was saying. You went down and you're like, nah.
we're just going to go down that same length. So go parallel to that vector, but go down the same length. So now it's right here. Okay?
I wonder if that's what I was gonna draw originally.
Wow. Maybe, probably. Sorry, I doubted you. Now, does it matter what order you do that in? What do you think? I don't think so. But let's keep going to see if there's a situation where it does matter what order. So what do we call that? We call that the commutative property of composite transformations, I guess, if it was a thing. But let's see. Let's just keep moving here. Okay. So see how that's two transformations resulting in still a congruent. This is still congruent to this. It has an opposite orientation. So it's like a reflection. So it's an opposite orientation, but it's still congruent. This side is congruent to this side. This side is congruent to this side, and this side is congruent to this side. Okay. All right, so two reflections across parallel lines. A composition of two reflections across two parallel lines is a translation. So if I had two parallel lines, okay, and I wanted to do a reflection of like this triangle, let's do this, let's just do a trapezoid. Okay, so let's reflect it across this line first. So it looks like this, right? And then I'm going to reflect this across this line, so that's a little bit closer here. So it ends up being, what is that? That's just a translation. It just shifted. That's just a translation. Now let's see if this is commutable. All right. Let's see if you can reverse that. What happens if you reflect this across this line? Well, that would put it way over here. So it would look like this. That's the first one. And then what we're going to do is we're going to reflect it across this line. And that would put it way over here. So see how those compositions are not reversible. That would put this one way over there. That doesn't work. Okay, so their order does matter when you're doing these reflections. All right. Now, another interesting thing is I could have drawn this trapezoid a little differently and drawn it like this. And that would have made this the opposite orientation. And right now that is not a translation, right? Because that's the opposite direction. But when I reflect this, look what happens. It goes back to the original orientation. Okay? So look, this is now a translation, but reflection across one parallel line is not a translation. But if you go two parallel lines, then it is a translation. What do you think will happen if you go three parallel lines? Is that a translation? Nope, because it's the opposite orientation. So what's your theory? If there are an odd number of parallel lines that you're reflecting over, it's not going to be a translation, but if there's an even number, it's going to be back to the original. Now, what could you call this though? This reflection is not a translation, but what's the other transformation called?
Transcription.
A rotation. Do you think this is a rotation? Well, no, because it's not upside down. So rotation doesn't really work. Okay. All right, now look at this. Two reflections across two intersecting lines result in a rotation. So now let's say that these are not parallel lines, but they're intersecting lines. Okay, watch this.
Yes.
Okay, let's reflect it. We're going to do the same reflection here, right here. And it's going to end up right here, right? That's the one reflection over that one line, right? Right? Good. Okay, now let's reflect this over this line, and it looks like this. You see that? Now look at this. Look at this. It's a rotation. It goes from here to here. And look where the axis of rotation is right there. So it goes from here to here. So when you reflect over two parallel lines, it's a translation. But when you reflect over two intersecting lines, it's a rotation. Okay, let's write that down. So two reflections over parallel lines results in a translation. But if it's over intersecting lines, it results in a rotation. Okay, see how I reflected it over this line? And it was the opposite orientation right there. And then I reflected again over this intersecting line. And it's back to the original orientation, but it looks like it shifted to like right there. So like 90 degrees almost. Okay. And I bet you there's a correlation with this angle here, which is probably about a 45-degree angle, and the rotation. The rotation goes like this. So that's a 90 degrees. Okay. All right. So transformations on a rectangle in the following order. So if you want to look at example 4 in your book, you can when you get home. But basically, when you have one reflection, yeah, the biggest thing that I want you to know is this right here. So when you do two reflections, so basically any transformation can be put together by just doing reflections. You don't have to rotate anything. You don't have to slide anything. You can just do reflection. So you can build any transformation, any reflection, or any rotation, or any transformation by just using reflections. Either reflecting over parallel lines for a translation or slide, or reflecting over intersecting lines for a rotation. Okay. All right. That's about it.
Black man, give me some math and I'll give you some flack. Black man.